All right, beginning our topic here on exponents. Going to look at several of the properties of exponents today. So first, starting with this warm-up. This warm-up is just wanting us to recognize really the effect of a negative number and the number of terms we're multiplying together here. So for the first one, we have negative 10 times negative 10 times negative 10. Well, those three multiplied together are going to give us 1,000. And when you have three negative numbers, an odd number of negatives multiplied together, your result is going to be negative. So we're going to get negative 1,000. For number 2, notice we're all multiplying tens again, but now we have 4 of them. We have an even number. So if we multiply an even number of negative numbers together, we're going to result in a positive answer. And that answer here would be 10,000. For the third one, again, now they're not all positive or negative. We have some of them. So count up the number of negatives you have. We have 3 negative numbers there. So that means we have an odd number of negative terms. So we're going to end up with a negative answer. And if we multiply 1 times 2 times 3 times 4 times 5, we're going to get 120. So we end up with negative 120. And then the fourth one, we have all negatives. And we have 4 terms, so an even number. So the answer is going to be positive. And you'll notice it's really no different as far as the numbers we're multiplying together. If you forget about the signs for a moment, as number 3, because the only thing 3 has extra is times 1, and times 1 doesn't change anything. So we're going to end up with positive 120. Okay, so some key vocabulary words we're going to be looking at when we're talking about exponents. Power, that's the exponent itself. The base, that's the, in simple terms, the large number that we're raising to the small exponent when you're looking at the size of it, just to identify it. And then the exponent itself. All right, so moving on to the getting started activity, just going to try to recognize some patterns here. This is talking about Jake, a dog, an English Mastiff puppy, or Jake adopted an English Mastiff puppy, I should say. His name's Rickson. The breeder provided documentation that verified Rickson's lineage for 3 generations as shown. So a dog's lineage is similar to a person's family tree. It's very similar. It's almost the exact same. We're just dealing with a dog instead of a person. And it shows the dog's parents, grandparents, and great-grandparents. So for the first one, how many parents does Rickson have? Well, just like a human, you would have 2 parents. So 2 parents and their names, it looks like were Cody and Bella. Okay, how many grandparents does Rickson have? Well, if we go to the grandparent generation 2, he has 4 grandparents. Each parent has 2. And if we go to the great-grandparents, each grandparent has 2 parents. So there would be 8 great-grandparents in generation 3. So what pattern is there for the number of dogs in each generation? We are doubling the number of dogs from the previous generation. So when we look at generation 3, we took the number in generation 2, which was 4, and doubled it, and we got 8. All right, so continuing with that, we're going to use that on this page, so we'll refer back to it multiple times. Jake wants to trace Rickson's lineage back 7 generations, see how many sires, the male parent, and how many dames, the female parents, are there in 7 generations of his lineage. Well, we know generation 1, his parents, there was 2, and we know it's doubling. So 4, 8, times 2 would be 16, times 2 would be 32, times 2 is 64, and times 2 is 128. So if we broke that down further in extended form, and this is what would be called, and the next page is going to ask us to label it, so I'm going to go ahead and do it now, expanded notation. So 2 is just 2 to the first power, and here's the power we're going to look at. So the second generation had 2 times 2, so that was 2 to the second power, and then we continue with that. The third generation had 2 times 2 times 2, so 2 to the third power, And I could go ahead and keep filling in the powers, then I'll go back in and fill expanded notation. So then we're going to have 2 to the 4th, 2 to the 5th, 2 to the 6th, and 2 to the 7th. So we can think of that's the number of 2's we're going to be multiplying together. So here's 4 of them, then 5, and 6, and then 7. Okay, so an expression used to represent a product of repeated multiplication is called a power. So a power has a base and an exponent. So the base of a power is the expression that is used to factor in the repeated multiplication, and the exponent is the number of times that base is being used to factor in repeated multiplication. So in other words, we are taking a base and multiplying it by itself the number of times the exponent tells us to. So like that worked example, you can write a power as a product by writing out the repeated multiplication. 2 to the 7th is the same thing as 2 times 2 times 2 7 times, which is exactly what we were filling in up above. Okay, so on the next page, we already did 2 and 3. It's why I said I was filling in those columns. We labeled that third column expanded notation, and then we labeled the fourth column of the table the power. And then we wrote each generation as a power. So we already did fill those in. So for 4, how many dogs are in Rickson's lineage in the 12th generation? Well, all we'd be looking at is 2 to the 12th. And again, we don't have to sit here and multiply that out 2 times 2 times 2 12 times. If we go to our calculator, we can hit 2, and then the exponent button is that little up arrow looking button just above the divide sign, and then we can type in our exponent. Now notice the cursor is still up there in the exponent. If you wanted to add anything else into the expression, which we'll see later on, we want to use the right arrow, and if you touch that, it'll move back down to the level of the base. But 2 to the 12th, and then we can hit enter, and that is 4,096. So in the 12th generation, just as a lot of dogs, there we go, we have 4,096 dogs. Okay, 5 asks us, how many total sires and dames are there in all 3 generations shown in Rickson's lineage? So, well, in the 3 generations shown, we had 2 parents, we had 4 grandparents, and then we had 8 great-grandparents. So if we add those together, there was a total of 14 dogs in those 3 generations. All right, so we're going to look at 1.2 now, practicing with some powers. So again, I'd practice putting these in the calculator, and especially when we get to the negatives, we're going to talk about those. So 5 to the 3rd, we can write out, so well, we're identifying the base and product, and then we're writing it out. So we're going to have 5 times 5 times 5. But if you put that in your calculator for practice, we're going to get 125. So you can do that with each one if you want to expand it. And then we're going to talk about the calculator part, like I said. So on B, -9 to the 5th. We have to make sure if we're raising a negative number to an exponent, we put it in parentheses in our calculator. If we do not, if we just type it in as -9 to the 5th, what the calculator reads that as is -1 times 9 to the 5th, which you're going to get lucky and get it right when the exponent is an odd number. But as we saw from that warm-up, an even number of negatives multiplied together is going to give us a positive answer. So we have to make sure and put that in parentheses when we go to our calculator. So -9 to the 5th, the way we're going to type it in is parentheses, -9, close parentheses, to the exponent of 5. And you're going to get -59,049. So -59,049. Now, you notice C is different. C's got -11. It's not in parentheses raised to the 3rd power. So we don't want to put that in parentheses. We don't want to put parentheses where there's none there. Where this one, actually, we do want the calculator to read as -1 times 11 to the 3rd. And if you put that one in, test it out, you should get negative 1,331. And then if we were to simplify the next one, 4 to the 5th gives you 1,024. 3 to the 6th should give you 729, and then we can multiply those together. But also, we can type that whole expression in as 1 in the calculator, not have to simplify it piece by piece. So if I go back to the calculator again, I can type that in as 4 to the 5th. That's where we got to use that right arrow now to move my cursor down, times 3 to the 6th. And now it takes care of that for us without having to multiply just 4 to the 5th and 3 to the 6th and then multiply those two results together. We can do it all at once, and there's our answer. So if we go back to fill that in, that was 746,496. All right, so number 2 is emphasizing what I was talking about with the negatives. If we have a negative, not in parentheses, raised to these exponents, and we put those in the calculator, it's going to read every single one of these as negative 1 times 1 to whatever the exponent is. And that for all that first row, A, B, C, D, you can try it yourself, put it in your calculator. They're all going to give us negative 1. Now, if we put it in parentheses like E, F, G, and H and include the negative in what we're raising to the exponent, now we're going to go back to that rule we saw with the warm-up. An even exponent, multiplying an even number of negatives together, gives you a positive answer. So negative 1 to the 2nd power gives you an answer of positive 1. So will G, negative 1 to the 4th power. That's an even number, so that'll be positive 1. But if we look back at F and H, to an odd number exponent, those are both going to result in negative answers. So we'd get negative 1. So what conclusion can we draw about negative number raised to an odd power? Is the result will always be negative. And then for 4 is the opposite. What conclusion can we draw from a negative number raised to an even power? The result will always be positive. Because an even number of negative numbers multiplied together gives you a positive answer. All right, so we are actually going to skip past 1.3, which is the next 2 pages. And we are going to go to 1.4, and we're going to look at the product of powers rule. It says in this activity, we're going to explore different expressions to develop rules to evaluate powers. So it wants us to rewrite each expression as a product using expanded notation, then identify the base or bases and record the number of times that base is used as a factor. So in other words, if we look at A, 2 to the 4th times 2 to the 3rd, we could say that's 4 2s times 3 2s. So if we count up the number of 2s there, that is 2 to the 7th. Okay, for the next one, same idea. It's 3 negative 3s times 3 more negative 3s. If we count those up, we get 6. So negative 3 to the 6th. And it was in parentheses, so we're keeping it in parentheses. Okay, for C, that first 4, if there's no exponent on it, that's to the 1st power. So this is 1 4, 4 to the 1st, times 5 more. Now if we count those up, there is 6. So 4 to the 6th power. And then for D, if we look at just the bases that are 5s, so this is like having 5 times 5, 2 of them, times 3 more 5s, times, move down to the next row, 2 6s, so 6 times 6, and then times 6 to the 1st. So if we count those up, there is 5 5s, so we have 5 to the 5th times 6 to the 3rd. There's 3 6s there. And similar on E, 9 to the third would be 9 times 9 times 9. There's also a 9 to the second, so 2 of them. And then we have 4s, so 4 to the second, 4 times 4, and 4 to the fifth, so 5 more 4s. So if we count those up, the number 9's there is 5, so we have 9 to the fifth times 4 to the 1, 2, 3, 4, 5, 6, 7, so 4 to the seventh. Now, if we look at how we could get to that pattern, I already kind of for 2, I already answered the question for each A, B, C, and D. I wrote after the expanded form, I went ahead and filled in simplifying the exponent. So what I just underlined is our answer really for 2. Okay, but 3 says, what's relationship can we notice between the exponents in the original expression and the number of factors? Well, if you look at A, for instance, 2 to the 4 times 2 to the third, and we ended up with 2 to the seventh. So the way we could get to 7 was be adding up the exponents of 4 and 3. So for 3, we could say the number of factors is a sum of the exponents. Okay, so if we wanted to write a rule we can use to multiply powers, is we're going to add the powers with the same base. So in other words, 2 to the A times 2 to the B, we could rewrite as 2 to the A plus B. Because the base of 2 is the same, as long as the base is the same, we can add those exponents together. Okay, so in this worked example, for the next rule we're looking at, is what we call a power to a power, power raised to a power. The exponential expression 4 to the second raised to the third is a power to a power. It can be written as a two repeated multiplication expression using the definition of a power. So in other words, if we have 4 to the second, like that worked example shows us, then raised to the third, that's 2 4s 3 times. So if we use that rule and try to work out these examples, this is like saying 2 8s 3 times. And if we count up the number of 8s there, we now get 8 to the 6th. So for B, this would be like having 4 5s 2 times. So if we count up the number of 5s there, there's 8. So 5 to the 8th. And then for C, now that negative is outside the parentheses, so that's like having just -1 out there, times 6 to the first, so just 6, but 6 times. So 1, 2, 3, 4, 5, and 6. Okay, so we end up with -1 times 6 to the 6th. So we could say -6 to the 6th. Just don't put your negative in parentheses with the 6 because it's not included. It was outside to start with. Okay, as opposed to D, now that -6 is in parentheses. So this is saying -6 times -6 2 times, done twice. And if we count those up, there's 4. So we end up with -6 to the 4th power. Okay, so the relationship we can notice there, if you look at the exponents, say back on A, 8 to the second raised to the third, and we ended up with 8 to the 6th. So the way we can get to 6 from exponents 2 and 3 is multiplying those together. So we could say the number of factors is the product. So we're multiplying them of the exponents. So if we wanted to write a rule for that, if we had 2 to the A raised to the B, That would result in 2 to the a times b, multiplying your exponents together when you got a power to power. And one other way you can think about it, I always describe, now it's not technically distributing, but when we see distributing, it's a number outside the parentheses. That's what we're doing here. We're just distributing exponents to the exponents inside the parentheses. Okay, so using the rules we know, it's important to be able to recognize the difference of when do we add our exponents, when do we multiply them. So if with a on the next page, we're multiplying the same base together, 6's. So this is when we add exponents. So this is going to become 6 to the 7th. If we check B, same thing. Multiplying the same base of 9, so we add the exponents and get 15. For C, now we have one base of 4 with a power raised to a power. This is where we multiply our exponents. So 3 times 5, we get 4 to the 15th. Okay, and then D, those are not the same bases, 2, 3, and 8. So we can't add any exponents. The most we can do there is multiply 2 times 3 and get 6, and then times 8 to the 5th. So that's the simplest form without completely putting it in the calculator to get our final answer. That's just simplified. Now E is back like A and B. We got the same base, 5 being multiplied together, so we need to add all our exponents. Key being, just don't forget this 5 has an exponent of a 1. So 5 plus 2 is 7, plus 1 is 8. So this would be 5 to the 8th. And for F, we have power to a power rule. Now both the 2 and the 3, if there's no exponent on them, it's like having a 1. So we're going to multiply that 4 by both of those exponents, and we end up with 2 to the 4th times 3 to the 4th, using our power of a power rule. All right, on number 9, Ramon says 2 to the 6th equals 12. Randy says 2 to the 6th equals 64. Who is correct? Well, 2 to the 6th is 64. So Randy is correct. And the mistake Ramon made is a common mistake. Ramon multiplied 2 times 6 instead of multiplying 2 times itself 6 times. Very common mistake. You got to be careful about that. And then Isabel says 2 to the 2nd plus 2 to the 3rd equals 2 to the 5th. Elizabeth says that 2 to the 2nd plus 2 to the 3rd does not equal 2 to the 5th. Who is correct? Well, Elizabeth is correct. And another common mistake is being pointed out here. The product rule is when the bases are being multiplied together. This is addition. So Isabel applied the product rule to a multiplication problem. Oh, sorry, to a addition problem. It needed to be a multiplication problem. To an addition problem. Sorry about that. It needs to be a multiplication problem to be able to add our exponents together. And this was not. It was an addition problem. All right, next rule we're going to look at on the next page, activity 1.5, quotient of powers. So we're looking at dividing bases now. So it says write each numerator and denominator as a product, then simplify each expression, write these simplified expressions. In other words, if we expand these out, I'm just going to do 2 of them for the space. We'll do A and then C. So on A, we have 5 9s, 1, 2, 3, 4, 5. And then we have 2 9s in the denominator. So if we could think of canceling out a 9 in the numerator for every 9 in the denominator, we could cancel here and here, and we're left with 3. So that becomes 9 to the 3rd. So again, we're going to do C. So if we did the same thing on C, we got 10 8s in the numerator. 8 10s. 3, 4, 5, 6, 7, and 8. In the denominator, we have 6. 1, 2, 3, 4, 5, and 6. So again, if we cancel out 1 in the numerator, for every 1 we can cancel out in the denominator, well, what we're left with is 2. So 10 to the second power. So the relationship we want to notice there, we ended up, for instance, if we look at C, 10 to the 8th over 10 to the 6th, and we ended up at 10 to the second power. So how can we get from 8 and 6 to 2? We'd subtract those exponents. So we subtract the exponent in the denominator from the exponent in the numerator. So in other words, a rule we could write here, if we have 2 to the a over 2 to the b, again, the bases need to be the same. That will result in 2 to the a minus b. So if we want to simplify these using that rule, for a, exponents are 8 and 3. The bases are the same as 6. 8 minus 3 would give us 5. Okay, for b, bases of 9, negative out front, it's like multiplying by -1. 7 minus 5 gives us 9 to the second power. And on C, what we need to notice, we cannot subtract those. We do not have bases that are the same. One base is a 2 and one base is a 3. So I just make a note that bases are not the same. So we cannot subtract those exponents simply because those bases are not the same. All right, next, looking at powers that are equal to 1 and numbers less than 1. So you notice where it's in that first row there, where it's showing 4 over 4, 9 over 9, 25 over 25. A number divided by itself is going to give us 1. So if we rewrote those with exponents, all those are to the first power. It's like having 4 to the first over 4 to the first, 9 to the first over 9 to the first, or 25 to the first over 25 to the first. Now, if we simplify that using our rule where we just subtracted our exponents, on each one of those, 1 minus 1 gives us 0. So 4 to the 0, 9 to the 0, 25 to the 0. So we can conclude any base raised to the 0 power ends up as a result of 1. So any base to a power of 0, the result is 1. All right, so from there, on to our next page. We're going to start looking at what would happen with negative exponents. And that'll be the second one we get to, number 5 on here. So first, number 4, let's start with 1. And we're going to multiply by 10 3 times. So if we start at 1, that's 10 to the 0 power would be 1, like this is showing here. If we multiply that by 10, it's like 10 times 1. So we end up with 10 to the first power. If we multiply it by another 10, 10 times 10, that would be like saying 10 to the second power. And if we multiply it by another 10, 10 times 10 times 10, we get 10 to the third power. So what is happening to the exponents as the number becomes greater? The exponent becomes greater. And then we could go the opposite way too. What if we divided by 10? So if we start out at 10 to the 0, which is 1, or 10 to the 0, which is 1, and we divided that by 10 like it's showing in the first row, we get 1 over 10. So we could think of that as 10 to the 0 over 10 to the 1. And if we follow our subtracting our exponents rule, when we're dividing with the same base, that ends up as 10 to the negative 1. Okay, if we divided it by another 10, so 10 times 10 in the denominator is now 100. We could think of that as 10 to the 0 over 10 to the 2. 10 times 10, which would turn into 10 to the 0 minus 2. In other words, 10 to the negative 2 power. And then if we divide it by 100 one more time, 10 times 10 times 10, we get 1 over 1,000. And again, we could think of that as 10 to the 0, which is 1, over 10 to the 3. And if we subtract our exponents again, 0 minus 3, we get 10 to the negative 3. So what is happening as the exponent as the number is getting smaller, that fraction is getting smaller, the exponent is getting smaller. It's going the opposite way. So when the number gets bigger, the exponent gets bigger. When the number gets smaller, the exponent gets smaller. So if we wanted to write each one of those as a decimal, 10 to the negative 1, you could try to put that in your calculator, you're going to get 0.1. 10 to the negative 2, you're going to get 0.01. So you notice the decimal from 1 is moving to the left, the negative direction, one placeholder. Every one of those goes up. So we could predict 10 to the negative 3. Oop, it all disappeared on me. I'd rewind the video if you need to fill those in. I'll refill in the one we're working on C here. So that was 10 to the negative 1 is 0.1. 10 to the negative 2 equals 0.01. And then 10 to the negative 3, I was saying we could predict the decimal would go 3 to the left and be 0.001. All right, so you keeping that in mind as we move on to 6. We're going to rewrite each sequence as a number using the definition of powers. So if we think of anything to the 0 power as 1 and to the first power is itself. So we could say 2 to the first power is 2. If we went backwards, 2 to the 0 power would be 1. 2 to the second power would match up with 4, and 2 to the third power would be 8. So going backwards the other way to those fractions, 1/2 would be 2 to the negative 1. 1/4 would be 2 to the negative 2, and 1/8 would be 2 to the negative 3. Okay, and we could fill in the same thing for 3. It would be very similar, same exact exponents, but we'd be dealing with a base of 3. So if we go down to C, describe the exponents in the sequence. Again, it's just emphasizing as the number becomes greater, the exponent becomes greater. All right, so if we now use that rule of subtracting our exponents, 10 to the 0 over 10 to the 3 is 0 minus 3. We get 10 to the negative 3, which is 0.001. For the next one, B, 0 minus 5, we get 10 to the negative 5, which is 0.00001. Decimal moved 5 to the left from 1. And then 0 minus 4, 10 to the negative 4, which would be 0.0001. So the decimal moved 4 to the left from 1. Okay, we could use that now to fill in that table. Actually going to skip past that. I want to get more to the examples of simplifying. We might come back to it, but I want to see first just straight up examples of what do we do with a negative exponent and make that connection before we get back to that table. All right, so I want you to skip to the next page on 9, and we're going to rewrite these powers to make the exponent positive. So a number is never simplified if it has a negative exponent. We have to leave the exponent positive. So what we do is we take a negative exponent and we move this to the opposite side of the fraction. So you could think of 8 to the negative 4th is over 1. So all we have to do is move it to the opposite side of the fraction, and it becomes 1 over 8 to the positive 4. And now that is simplified with a positive exponent. So same thing for the next one. 5 to the negative 6 becomes 1 over 5 to the positive 6th. And C, 7 to the negative 5th becomes 1 over 7 to the positive 5th. And then D, same thing, we just have two bases. So those are both negative exponents. So it becomes 1 over 4 to the positive 2, 3 to the positive 3. So we can use that rule to always leave a positive exponent. Now, all of those were in the numerator. We moved them to the denominator. If we start with a negative exponent in the denominator, we just move it up to the numerator. So for that first row in that table, 1 over 3 to the negative 2, it's going to move to the numerator and just become 3 to the positive 2, which gives you 9. Same thing for the next one. 4 to the negative 2 is going to move up to the numerator and become 4 to the positive 2, which gives you 16. 4 times 4. 1 over 5 to the negative 2 becomes the numerator and just becomes 5 to the positive 2, which is 25. Now, you'll see on the next one, they did it for us there. 2 to the negative 2 was in the numerator, moved it to the denominator, became 1 over 2 to the 2, which becomes 1 over 4. So for the next one, this would become 1 over 3 to the positive 2, and 3 squared, 3 times 3 is 9. And then the last row, one more, that would move to the denominator, become 1 over 5 to the positive 2, or 1 over 25. So describing how to rewrite an expression with a negative exponent in the numerator, we move the base to the denominator and make the exponent positive. And then the next one's going to be the opposite. How can we rewrite an expression with a negative exponent in the denominator? We move it to the numerator. So move the base to the numerator. So it's basically to the opposite side is always what we're doing. Opposite side from where it started on. And again, make the exponent positive. All right, so wrapping it up, all our rules here. We had product rule. When we're multiplying the same base, we add our exponents. These rules are actually even on your star formula chart. They give you these rules. Power to a power rule. We're raising an exponent to another exponent. We multiply our exponents. The quotient rule. Dividing to the same base, we subtract our exponents. The 0 power rule, anything to the 0 power was 1. And then negative exponents, we move them to the opposite, move the base to the opposite side of the fraction. If it started in the numerator, it goes to the denominator and vice versa, and then make the exponent positive. So to wrap up, be a good time, pause the video. The next 2 pages have several examples for you to work out, and then unpause it and check your work based off what you got. All right, so I'm going to work through these. So if we're looking at number 1, 2a to the 8 times 2a to the 6, we have 2 times 2, which gives us 4. And then we have 2 of the same base, the a's, so we can add those exponents. And that becomes a to the 14th, 8 plus 6. Very similar problem on number 2. 4 times 8, those coefficients, gives us 32. The b's, same base, so we add the exponents, 2 plus 9, and we get 11. 3, again, is the same thing. It's just we have 3 of terms. It's no different. So we have negative 3 times 5 times 2 for the coefficients, which will give you negative 30. Then for the c's, again, don't forget the c has an exponent of 1. If we add up the exponents of 9, 3, and 1, we get c to the 13th. Okay, for 4, we got our power of a power rule. Again, don't forget that 3 has an exponent of 1. So when we multiply n, we're going to get 3 to the 3rd over d to the 2 times 3, which is 6. And then you can simplify 3 to the 3rd. If you put that in your calculator or just do it in your head, you get 27. So 27d to the 6. Okay, similar on 5. We have to remember again that 10 and the e have exponents of 1. So for the 10, 5 times 1 becomes 10 to the 5th, e to the 5th, and then f, 5 times 3 is 15. So again, we can now simplify 10 to the 5th. If you put that in your calculator, you're going to get 100,000. So 100,000 e to the 5th, f to the 15th. Nothing changed with the variables on that last step. 6 now is using our subtraction rule, or quotient, or our quotient rule, where we subtract our exponents. Same base again, f. So 8 minus 3, and we get f to the 5th. For 7, our coefficients are 10 and 5, so we can divide there. 10 divided by 5 is 2. And then if we subtract our exponents, 4 minus 6, we get -2. So now we have a negative exponent. So we need to move that to the opposite side of the fraction. Again, think of it as being over 1. Now, a common mistake here is people will move that coefficient 2 with it. The exponent on the 2 is +1. It's going to stay where it's at in the numerator, and only the g to the second power is going to move to the denominator. So we end up with 2 over g to the second power. Okay, for 8, coefficients of 30 and 15, divide those and we get 2. The h's, 8 minus 2, and we get h to the 6th when we subtract those exponents. And then the last two on this page, again, we're dividing. So 35 divided by 7 gives us 5. And then our quotient rule, we subtract our exponents. For the I, 7 minus 2 gives us I to the 5th. But for the j, 3 minus 3 is 0. So anything to the 0 power is 1, so those just cancel out. So we just get 5a to the 5th. And then the last one on this page, 10 a to the 2nd over a to the 5th, but notice all of that in parentheses is raised to the 0 power, and anything to the 0 power is 1. All right, and now the second page, 11, same base, and it's our quotient rule, so we subtract those exponents. We get 2 to the 2 minus 6 is -4. So then we have to move that to the opposite side, and it becomes 1 over 2 to the +4. And 2 to the 4th is 16. So it ends up as 1 over 16. Okay, 12 is back to multiplying our product rule. So coefficients of 4 and 3. 4 times 3 is 12. And don't let those parentheses confuse you. It's the same thing as writing it out like this and expanding it out. Does not change it. So 4 times 3 gives us 12, and then we add those exponents 2 and 5 and get x to the 7th. Okay, 13 again is our product rule. We're going to add those exponents. So 4 plus -5 gives you -1. So we move that to the opposite side of the fraction, becomes 1 over 9 to the +1. And if it's a 1, you don't have to write that exponent there again. All right, 14. If we add those exponents together, 0 and -2, we get -2. So move that to the opposite side to make that become a +2 exponent. And 8 to the second power, 8 times 8 is 64. All right, for 15, -3 minus -3 gives you 0. Essentially, these cancel out, and this just becomes 1. So 3 to the 0 power is 1. Okay, 16. These tend to trick people up because we got so many negatives. If we think of -2 minus -3 for subtracting our exponents, that gives me +1. So this just turns into 4 to the 1st, which is just 4. Again, if you have struggle subtracting those, just plug it in your calculator. -2 minus -3. Okay, then 17, subtracting again with our quotient rule because we're dividing there. So -3, 2 minus 4 gives you -2. So that's going to turn into 1 over, when we move it to the opposite side of the fraction, -3 to the +2. And -3 squared, -3 times -3 is 9. So 1 over 9. Okay, 18. Subtract those exponents again because we're dividing with the same base of h. 3 minus 5 is -2. So we move it to the opposite side of the fraction, becomes 1 over h to the +2. And our last two, subtracting again. Oop, lost my page. Let me go back. Again, if you need to fill those in, just go back and fill those in. Rewind the video. So our last two, 19 and 20. 4 minus 5, we get x to the -1. So again, move that to the opposite side of the fraction. Becomes 1 over x to the first power. And then 20, the bases of m's. We subtract those exponents. Since we're dividing there, you get m to the -2. For the p's, -2 minus 3 gives you -5. So those are both negative, so they both move to the opposite side of the fraction. So when there's nothing left in the numerator, we just put a 1 up there. So m to the second power over p to the 5th power. Those change sides. All right, so there covers all our exponent rules from our product rule, our quotient rule, power to a power, zero exponents, and negative exponents. All the rules we looked at today.